All right, so now we're on to lesson 2. So in lesson 1, we really looked at the graph of the exponential function and a logarithmic function, and we realized that the relationship between the two is that they're inverses. So now we're going to look at what is the significance of them being inverses. So I thought I would go ahead and just kind of remind us of what the graphs look like. The graph that is increasing upward in blue is the exponential function, and this graph in red is the logarithmic function. Couple of things I want us to remember that we talked about in lesson 1 regarding exponential functions. So remember what we said about the base. The base of an exponential function has to be greater than 0, which means b has to be positive, but b can't be 1. 1 is the only positive number that it cannot be, because if the base is 1, 1 raised to a power, any power is going to be 1. So that would be a constant function and not exponential. We said that the exponent, the variable x, can be any real number. Its domain is negative infinity to infinity. And in a lot of college textbooks, you'll see the notation x is in the set of real numbers. All right, and then we talked about y, the range. The range is 0 to infinity. So we could say that the y values will always be positive. Okay, and those are some important things. If you look at the graph, remember the graph does not go below the x-axis, so that means the y values are always positive. Okay? All right, so since exponents and logarithms are inverses, that means that these same restrictions for the exponential function will be the same restrictions for a logarithmic function. Now, I've decided I don't want this on there. Yours does not have it. I just didn't take it off of mine. And I wanted to use, your copy doesn't have that y equals b raised to the x power either. That just wanted to remind us that these are characteristics for the exponential function. They are also characteristics of the logarithmic function. The base b for a logarithmic function, the base has to be greater than 0 except for 1. The x values, which your x values will be here, will be any real number, negative infinity to positive infinity. And your y values will always be positive. They will always need to be positive. So you may be wondering, where does y equals log base b of x come from? How do we go necessarily from this version to this version? And in lesson 3, you're going to see how this equation is derived from this equation. But for now, just remember that y equals log base b of x is a logarithmic function. So, because these are inverses, that means that we can take any exponential expression and write it in logarithmic form, and we can do the same thing with logarithmic functions. So we'll start with rewriting 3 squared equals 9 in logarithmic form. So, all right, so here is how you basically convert exponential form to logarithmic form. Your base b is 3. So you have log base 3, and of the answer, 9, equals 2. So when you take an exponential expression and you want to convert it to logarithms, it will be log log of this base, or to this base, of this number equals the exponent. So in logarithmic form, x, remember, is your exponent, and this is your answer. So log base 3 of 9 equals 2. All right, let's do this one. And let's do this one. So we have 1.2 raised to the third power equals m. We can write this expression in logarithmic form. We can take, it'll be log base 1.2, and that's fine because the base simply has to be greater than 0. So it's log base 1.2 of the answer, which in this case is m, equals the exponent, 3. So log base 1.2 of the answer equals the exponent, okay? All right, then how about e raised to the b power equals 9? Now this is just some exponential expression. Your logarithm would be log base e. So log base e of the answer, which is 9, equals the exponent b. And then what about this one? And by the way, does 5 to the negative 1 equal 1/5? Yes, it does. So we can write this using logarithms. It would be log base 5 of the answer, 1/5, equals negative 1. Okay. Okay, so now let's take a look at the next one. Now I want us to take a logarithmic expression and write it in terms of exponential, an exponential form. So our base is 6, our exponent is 2, and our answer is 36. So it's base raised to a power equals the answer. And hopefully you look at this and it makes sense. Would be my hope that you see. All right. So now let's do this one. We have log base 1/2 of 8 equals negative 3. So this would be 5. What am I doing? Wrong problem. This would be 1/2 raised to the negative third power equals 8. So it's base raised to power equals exponent. Okay. All right. All right, then notice what we have here. We've got another, this is not a typo. This is considered to be a natural logarithm. And a natural logarithm, you see natural logarithms, a lot in the sciences. But a natural logarithm, notice that there's no indicated base. It's because the base is understood to be e. Okay, so in your assignment for lesson 1, we discovered that e, if you recall, is approximately 2.71828, and so on. And so e is an irrational number that is between 2 and 3. Okay, so we have this understood base. This is an ln log with an understood base of e. So to rewrite this in exponential form, you still take the base, you raise it to the power of x, and you set it equal to the answer of 4. Okay? All right, so now let's look at the natural log of 1 equals 0. Okay, and this is a fact that the natural log of 1 equals 0. So how do we rewrite that in logarithmic form? You take your base, raise it to the 0 power, and that equals 1. Does this make sense? E to the 0 equals 1. Well, it should make sense because you've learned a long time ago that anything raised to the 0 power is 1. And that includes E. Okay, here's another one. The natural log of E equals 1. If we rewrite this in logarithmic form, we would have the base, which is understood to be E. Now remember, this E does not represent this E. It's the base of E, and E raised to the answer of 1 equals, or E raised to the power of 1 equals E. And that makes sense. Okay? So there's a couple of things that will be helpful to remember, and that is that the natural log of 1 equals 0, and the other is that the natural log of E equals 1, because those are some things that occur frequently, and knowing those values will make things a lot easier. All right, so now let's take a look at this expression right here. So let's say you're just simply asked to evaluate log base 2 of 8. So as you think about this, how would you evaluate this? How would you process this in your brain? Well, think of it this way. You're asking yourself this: 2 raised to what power equals 8? So when you think of it this way, you're asking yourself, what power do you raise 2 to get 8? And the answer is 3. Okay, let's do the one directly below it. The log base 5 of 25. Well, that would be 2, because you're asking yourself the base raised to what power is 25, and the answer is 2. Okay, so what about log base 3 of 1/3? So log base 3 of 1/3, how do you go from an integer to a fraction? Well, again, you're asking yourself, 3 to what power would equal 1 over 3? And that would be -1. 3 to the -1 would be 1/3. Now what about log base 1/2 of 64? So log base 1/2 of 64, you're going from your base is a fraction and it needs to equal an integer. So ask yourself, what if you did this? What if you said 2 to the -1? Is 2 to the -1 the same thing as 1 over 2? And it is. So what would I need to raise this 2 to get 64? And then that would be 2, 4, 8, 16, 32, 64. Wouldn't that be 5? So that would be 2 to the -5th power, which is 64. So notice this. Notice that going from integer to fraction in either one of those scenarios is going to leave you with an answer of negative, and that should be a -5. So whenever you go from an integer to a fraction to an integer, you know your answer will be negative. So here log base 3 of 1 over 27. You're going from an integer to a fraction, so that would be negative 3, because 3 to the negative third power is 1 over 27. So you have to train yourself to think about what the relationship is between logarithm and an exponent, or exponential form and logarithmic form, to be able to evaluate these. Can we do these on the calculator? And the answer is yes. And I will go through a couple of these in just a minute. But you cannot substitute using your calculator to find these values. You have to be able to think through and evaluate logarithms, especially the simple ones. Now, you can't do all of them, but you can do simple ones. So, for example, I'll pull my calculator back in, and I will open this up, and let's just say we want to evaluate log base 2 of 8, okay? I'm going to go to my home screen, and just as a reminder, if you go to Math, and you use your arrow key to go down and find A, you get log base, and you can type this in. Your base is 2, your expression is 8, and you get the answer of 3. If you remember how to change a logarithm to base 10, remember that would be log base 8, log of 8 divided by log of 2, and we'll do it that way. So log of 8, close the 8, divide by log of 2, close the 2, press enter, and lo and behold, look what we get. We get 3. So this version is very important. You end up, many times, you might end up with an expression that looks like this, and you need to be able to remember and to recognize that as being equivalent to log base 2 of 8. So you can do a lot of these problems with your calculator. I just encourage you to think through these, and you will have to be able to do this without a calculator. All right, so that concludes lesson 2, and we'll move on next time to lesson 3.